The second type of spectroscopy that we will study is going to be NMR spectroscopy, nuclear magnetic resonance spectroscopy. And so this video will give you an introduction. Certain nuclei, like the ones listed here in parentheses, have what we call a nuclear spin associated with them, which means that they possess a magnetic moment and they also have angular momentum. The two nuclei that we will use for organic chemistry are going to be the C13 and H1 nucleus. And really in the lecture portion of the course, we're only going to focus on the H1 nucleus, although in the lab, a lot of times you will learn about C13, and the discussion that we have about H1 can certainly be extended to C13. In the absence of an external magnetic field, these nuclear spins are randomly oriented. If you can picture these nuclear spins as being like tiny little magnets, and so we're going to represent them with vector arrows here. When there's not an external field present, these little magnets are just randomly oriented. However, when you apply an external magnetic field, the nuclei are either going to align with the field or against the field. And there's an energy gap created there. It's slightly lower in energy for the nuclei to be aligned with the field than against the field. This is a very small energy gap here, and it's an equilibrium that's established. And so keep that in mind, that there's not a huge difference between the two states. We can describe the energy gap mathematically with the following equation, where you have Planck's constant that I believe you've seen before in general chemistry. This other symbol here, this gamma, is the gyromagnetic ratio of the particular nucleus that you're observing. Of course, you have 2 pi, so all of this is just a constant. The other thing here is the magnetic field strength, and what we're really interested in is the fact that not only is this energy gap related to the magnetic field strength, but also to a certain frequency of electromagnetic radiation. What happens during the NMR experiment is that the equilibrium state is disrupted by applying electromagnetic radiation, and now you start disturbing this system. The nuclei that were in the higher energy state will now drop to the lower energy state, and the nuclei that were aligned in the lower energy state will go to the higher energy state. And with the radio frequency region of the electromagnetic spectrum is where this equation is satisfied, so we're talking in the megahertz region. When this happens and when this equation is satisfied, we say that the nuclei are resonating with the electromagnetic radiation, and therefore we call this type of spectroscopy nuclear magnetic resonance spectroscopy, or NMR spectroscopy. The most important takeaway from this equation, as far as you're concerned, should be the direct relationship between magnetic field strength and frequency. So if you have some magnetic field strength with a certain energy gap, and then you increase that magnetic field strength, you're going to increase the energy gap, and therefore you're going to need a higher frequency to satisfy this equation. There are really 2 ways you could satisfy this equation. You could either hold the magnetic field strength constant and vary the frequency, or you could hold the frequency constant and vary the magnetic field strength until you hit this state of resonance. Older instruments used that type of method where one or the other would be held constant, and they would sweep. So say they held the magnetic field strength constant, they would sweep the entire radio frequency range until this equation was satisfied, or vice versa, they could hold the frequency constant and sweep the magnetic field strength. Newer instruments use a different approach where the magnetic field strength is held constant, but then a pulse of energy that's in the radio frequency range is applied, and the pulse contains a range of frequencies in the radio frequency region. So this is how the equilibrium is going to be disturbed. You put it in the presence of the external magnetic field, you set up this energy gap, and then you disrupt the equilibrium by applying an RF pulse and getting these guys to switch states. After some time, it's going to relax back to the equilibrium conditions, but notice that there is, although exaggerated, there is a slight excess of nuclei going in one direction over the other. So it's exaggerated here. It's the difference in the energy states is actually very small, but it's very important because that's what the spectrometer is going to pick up on. So if you had the exact same number of nuclei going from the higher energy state back down to the lower energy state, as you did going from the lower back up to the higher to reestablish equilibrium, you would have a net result of no energy in or out of the system. But since there's a slight excess of nuclei relaxing back down, you are able to pick up on some radio frequency radiation being emitted during this relaxation process. And that's what the spectrometer is going to detect. Recall that there's a direct relationship between the magnetic field strength and the energy that's required, so the frequency that's required to satisfy that equation. And so if you have a larger field strength, the energy gap's larger, you need a higher frequency. So that means that different size magnets are going to lead to different radio frequency emissions in megahertz.